Hello, welcome again to the lecture series on control systems engineering. Now let us work out some more examples in this session. See, this block represents the controller K. This is the plant transfer function 1 by S into S plus 2. Okay, there's a summing point here or here. Okay, yeah, unity feedback system. So in the previous example, we discussed what should be the range of K so that the system will be stable. What is the limiting value of K at which system start oscillating? So as we vary the value of K from 0 to infinity, how the closed loop roots move, and we trace the locus, and at a given point or for a given value of zeta, how to determine the value of K and what are the corresponding transient response specifications we studied. We can also draw the response of the system by knowing these parameters. Also, at that point, steady state error is limit S tending to 0. S R of S divided by 1 plus G of S H of S. So for a given type of input, R of S is known. Once the K value is known, then G of S H of S here we can substitute. We can also find what is the steady state error for that system. That's fine. Now let us work out some more examples. G of S H of S is equal to K divided by S into S plus 1 S plus 2. I'll apply the rules and draw the root locus plot. First, better you take a good graph sheet. Then draw a spline. Okay. One, get range of mark like this. Okay. This is 0, 1, 2, 3, minus 1, minus 2, minus 3, minus 4, minus 5. 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. Okay. Next, there are 3 poles. So there should be no zeros. 3 root loci will be there. The root loci start from the respective poles. One pole is at S equal to 0. One pole is at s equal to -1. One pole is at s is equal to -2. Fine. So the root locus start from the respective poles, all should end at 0 in infinity, because there are no finite zeros. So let us draw the portion of root locus. Okay, on the real axis. Keep your reference here. To your right there is one pole, one is odd. So you go on moving your reference till it is odd. Now your reference is here, then to your right there are two even, no root locus. And again there is a root locus. Okay, draw like this. So mark the arrows indicating root loci start from respective poles. Good. The number of asymptotes are 3, n minus m. So they intersect at -1. Here they minus it. And you find the asymptote angles using the formula 2k plus 1 by divided by n minus m, that is 2k plus 1 into pi divided by 3. Go on substituting k values and get that. So one will be making 60 degree. So you draw a root locus at, asymptote at 60 degree. Say this is 60 degree. Here 180 degree and 300 degree. This is 60. This is 180. This is 300. Okay, you've drawn the asymptotes. Next, the root locuses between these two poles, you have to find breakaway point. So for that you have to consider the characteristic equation. Correct? Then differentiate this k and get the values. You are getting minus 0.423, 1.577. Minus 0.423 somewhere here. Mark the breakaway point. Other one is here, there is no root locus, so that is not a breakaway point. Next, it is obvious the root locus will definitely this will come here, break, so go asymptotically like this. Other root locus will go asymptotically like this. Another root locus will go asymptotically like this. So at what point this will break, intersect the imaginary axis? For that, form the root array and equate this to 0, you'll get k equal to 6, then form the auxiliary equation, find omega value, that is 1.41. So this is not proper, please, when you draw on the graph sheet it will be alright. So this is at 1.41, so my scale is not correct. Okay, here again 1.41. Okay, 4. So here at this point now k equal to 0. For what is the k value? K value is, I think, 6 now. Yeah, 6. K value is 6. K value is 6 here. Here k value is 0. Here also k value is 0. K value is 0. So now for any given zeta, you can mark the point, find k value, and required time response specifications we can find. And here you can write k tending to infinity. So asymptotes will help you in which direction the root locus should be drawn. So asymptotic means this will meet this line only at infinity. So this is how we can get the root locus plot of this. Simple. If you know the rules, we can go on drawing the root locus plot. Fine. Another example. Okay. Okay, sigma j omega. Yes, plane. Then mark all the values. Now let me look at poles. There is one pole at, so let me change the color. S equal to 0, S equal to -1, S equal to -3, S equal to -4. Okay, so use odd even principle now. Draw the root locus on real axis. Odd number of poles to your right, even number of poles to your right. Again. Okay. Mark the arrow. Mark the arrow. Mark the arrow. Mark the arrow. Now, 4 poles are there, no zeros, 4 asymptotes. Find intersection of asymptotes. That is found to be -0.2. The angles are 45, 135, 225, 350. -2. Okay. 45. 135. 225. 350. So it is 45 degree. Next 135. 225. 350. Okay, right. Then there should be a breakaway point here. There should be a breakaway point here. Okay. So find the breakaway point. So characteristic equation from here you find. It's a cubic equation. You have to find trial and error method. Okay, this is 0, -1. Okay, you just try -0.5. In this equation, you try with -0.5. So if you get net value negative, then you try a smaller value, say -0.4 you try. So you go on doing this trial and error. See here, -1 if I try negative, then minus 0.5 negative, so opposite sign. So then I decrease the value -0.4. So that way you go on doing the trial and error method. It takes time. Okay. So if you have now Newton-Raphson, so we can find those roots. That's not a problem at all. There are many methods to find the roots anyway, numerically. Okay, this is minus. Here you are going to get something like 0.43. Another is between 3 and 4. You have to try between -3 and -4. Try -3.5. You'll get positive, then increase them. -3.6, you'll get negative. That means somewhere in between it is. Okay, if you try that way, 3.58. So for one value you get negative, one value you are getting positive, means it is in between. Right. So try here now. It is -3.58. So whole logic is, if you plot a function for one value of say yes, you get positive. For another value of yes, you get negative. Then this point must be in between. Okay, right. So when I try with -3.5, you'll get a positive value. When I try with 3.6, I'll get negative value. That means in between. Then I'll try between 3.55, 56 like that. Then approximately I'll get this equation equal to 0. So that is little time consuming. You need to be careful about that. Yeah, I got a point here and another breakaway point here. I got it. After that, let us find the k value. So characteristic equation. Then from that omega I'll get 1.22. Mark 1.22. Maybe here it is. -1.22 is here. No. You draw the root locus so that every point on the root locus must make an angle of 180 degree and magnitude should be 1. That is difficult to do that way. So it's just an approximate plot. Okay. Same way here we will draw now. Like this. So k tending to infinity. You'll get this. So write k value. Here it is omega so much, omega so much, and k value you write whatever you get. That's the root locus. There are 4 poles, 4 root loci. Okay. So same way here, C of s by R of s is given. I should get G of s. I'll get this. Now there should be 4 root loci. I think the same way, follow the procedure, you'll get the root locus plot. right? In this example, there is one 0. So one root locus should end at 0. So let me draw it off. S equal to 0, S equal to -1, S equal to -2. Here there is a 0. Okay. So there is root locus here. Applying the principle I explained, there is root locus here. The arrow should be like this. This arrow, this will go like this. Root locus starts from pole, end at 0. Of course, here k equal to infinity. There are 3 poles, 2, 0. 2 asymptotes you get. Find the intersection of asymptotes. Okay, the intersection of asymptote happens to be sum of poles minus sum of zeros. You are getting +3. +3 you are getting. So again 1, 2, 3. Let us say somewhere here you get. One asymptote makes an angle of 90 degree, other makes an angle of 270 degree. Then you find a breakaway point. You will get a breakaway point here. Okay. So this should go like this. It will break at this point. Go asymptotically like this. Sorry, like this. Okay. All right. Okay, that's how we can draw the root locus and mark all the relevant values. Here there are 2 poles and 1 0. So here as it is, it will break here. Then you will get a break-in point at this point when you do the breakaway points. So these two will break. When you do you do not have to separately calculate breakaway point and break-in point. So when you do this, you are going to get 2 values here. -4.76 here, -9.23 here. That will act as a break-in point. So there is only one asymptote. So this will go here. Maybe it will go here. End at 0. Other one will go to infinity along this asymptote. That's it. Okay. The same way, in this case, no asymptotes are there. There is one breakaway point. There is a break-in point. Right. You can see these values of K system will be stable and these values of K system will be unstable. Okay, fine. Because there is +1. There's a pole at +1. And there is a pole at -1 here, -0.1. Is the root locus. Here there is root locus. K equal to 0 here. Okay, then this will go like this as the k increases. Then when it is 0.62, further if you increase, it will move to positive side. I think this omega value, k value is must be where? How much is that? This must be equal to 0. Point. Okay, it's 0.3. K value 0.3. More than that, it will move to stable region. Okay, this is how we can work out these examples. But it is quite tricky. These are simple. In the next session, I'll show you some tricky examples. Okay.